Welcome back to Math 130, Applied Algebra and Trigonometry. Let's continue with logarithms of base 10. Let's look at something a little more challenging. Let's look at the log, base 10, so the common log, of the tangent of 12.6 degrees. We haven't worked with trigonometry right now, but we're just putting this into the calculator. And here's the sequence of keys that you'll need to use to put it into the calculator. And when you put that into the calculator, you will find the answer to be negative 0.650671, or more digits if you have your calculator set slightly differently than mine. But we only need 3 significant digits, or we need to interpret those 3 significant digits into our answer, because since this is a logarithm, we're not going to go with just 3 significant digits. We're going to go with 3 significant digits to the right of the decimal. In this case, it's the same, whether you're counting significant digits or just significant digits to the right. But technically, because it's a logarithm, we want 3 significant digits to the right of the decimal, and that rounds to 0.651 or 651 thousandths, and it is negative. We will call that example 1 for this video. Okay, and let's clean this up a little bit. Come on. All right, let's look at an example 2. And let's work with the log of 500 minus the log of 20 equals the log of 25. And all of those are common logs. There's no base listed, so we assume it's a base 10. Therefore, it's a common log. Now, you may be given a problem like this, and you may be told to use your calculator. Okay, and you're going to be using your calculator to verify this equation. So what you want to do is to use your calculator to prove that the common log of 500 minus the common log of 20 equals the common log of 25. So to use your calculator to do it, you will just enter this into your calculator and find out that it is 1.398. And if you enter the common log of 25 into your calculator properly, you will get 1.398. Therefore, it is true. Just for practice, let's go back and do this as we have done it previously. Let's work this out. Okay, so we have a difference of 2 logs. The quotient rule tells us that that can become the quotient 500 over 20. And that would be equal to the log of 25. Well, it turns out that 500 divided by 20 is 25. So it also checks by that method. Okay, so let's work on some other things now. Now we've looked at equations like this. The common log of 100 equals 2. And if we remember that the common log has a base of 10, we can convert this into exponential form. The interesting thing is that that conversion to exponential form, okay, where each piece goes like that, moves into the indicated position, is the inverse of the log, the common log that we originally had. So on the left-hand side, we were taking the common log of 100, whereas on the right-hand side, we were raising 10 to the second power. So on the left, we read that as the common log of 100. And on the right, another way to read that is the anti-log of 2. So, if someone asks you to take the antilog of 14. Okay, let's not make it that big. That's going to be a little difficult here. Let's say the antilog of 6. Okay, all you would do is say 10 to the 6th equals 1 million, because 10 times 10 times 10 times 10 times 10 times 10 is 1 million. Also, you should know that instead of using the term antilog, sometimes it's called the inverse log. The terms are interchangeable. So, example 4. Take the inverse log. Remember, inverse log and antilog are the same thing, of 0.929. Now, you may also see the inverse log or the antilog written this way, with a -1 seemingly as an exponent of the log, but it actually means the antilog or the inverse log of 0.929, which is our example. So that is equal to 10 raised to the 0.929th power. And that is 8.49 when you plug it into your calculator. Now, what about significant digits going this way, taking the antilog? Well, when you're taking the antilog, we're using the rule in reverse. So let's look at that in example 4. We are taking the antilog of 0.929. That's 3 significant digits to the right of the decimal point. So 3 significant digits total is what you want in your answer. And actually, the number that came out of my calculator when I did the calculation, had a 1/8 out here. So I had already taken into account the rule and removed those 2 numbers. Perhaps you're asking how to put that into your calculator. It would be 10 caret, the caret button, 0.929. And that will give you this answer once you round it. Okay, let's move some things out of the way and go on to our last topic for this lesson, and that is the change of base formula. This is a useful algebraic technique in case you are ever separated from your TI-89. And this change of base formula looks like this. Let's go back to using the different colors. So log base b of x equals, all right, so for any base, you can convert this actually to any base you want to. Say base C instead of base B, okay? And this will be x up here, and below you will have the log base C of what was originally, okay, your base B. It's now going to become the argument. So if you just want to use the common log, because it's easy to do on your calculator, whatever, I'm going to remove the colors from this now. The log base B of x, whatever you have there, you can convert it to the common log of x over the common log. Please note that when you do the change of base, the former argument goes into the numerator and the base goes into the denominator. Look at the way they are positioned in our original log here. Log base b of x. The b is below the x, right? So it goes below the log of x. It goes into the denominator. The base goes into the denominator. The argument goes into the numerator. All right, an example of that. Let's go back to white. An example of that. This would be example 5. Log base 3 of 16 would become the common log of 16 over the common log of 3. Okay? If you really wanted to, you could change it to a different base. You can make the log base 3 of 16 equal to the log base 72 of 16 over the log base 72 of 3, as long as you have the same base in the numerator of your new fraction as in the denominator. Here we have a base 10 assumed and a base 10 assumed in the denominator. I do not know why you would ever want to convert to the base of 72, but hey, if it floats your boat, go ahead. And that concludes the discussion of the logs of base 10 for today. I will see you soon.